Hey, you guys, let me show you something that I need you to know for the assignment from our textbook on exponential functions and how you write exponential functions. Ask me in class where you can find this page. I won't give it out over right now, but I do want you to know that I'm going to work the question 1A for you. Each table shows a population of a city over a 3-year period. Write an exponential function to represent each population as a function of time. And of course, on the banners behind me are different poster notes that we have about writing exponential functions and where they come from and whatnot. You got to be an expert at them. But let me just dive right in here on 1A and show you the resource that's going to save your sanity as you work through these problems. Here, let me open up our perfect resource, DESMOS. Okay, here goes. Now, what you have here in front of you is all of the screen in front of us. I want you to click on the plus sign and then select table. Okay, here we go. For the table that opens up, now we're going to put like this 1A Blueville. We're going to fill the column X1 with 1, 2, 3, and then the Y1 column with the numbers across from 1 and across from 2 and across from 3. Okay, take the time to do that. Now, what should happen is that you should see a sequence of points representing row 1, row 2, row 3 showing up on the grid. But let me do a little bit of movement of this over here. They're not there. And so this is part 1 of this sequence of things I got to show you about Desmos that you got to know. And I'm going to have to let you know you need to use the wrench icon to mess with the domain and the range interval so that we can eventually bring those 3 points from the table into our graph space. So over here on the side, I'm going to click the wrench. And then when I do that, there's going to be some X's and Y like spaces that we're going to have to use. So like right here, I have -10. You know, my X numbers, they only are 1, 2, and 3. I don't need to go to the left so far. So I'm going to say -1. That just shows enough of the Y axis. Then for the X axis, our numbers aren't bigger than 4. X in the X column is 1, then 2, then 3. So I don't know, pick a nice number that's a little bit bigger than 3. Nice would be like a multiple of 5 or a multiple of 10. And immediately the really cool thing about Desmos is it's responding to that input. In the y-axis, the lowest number that our y-axis goes to down here is that -14.365. And then up here, it's at 14.365. But look at the y numbers. That Y column, the numbers are up to 7,300. So what we need to do is maybe a little bit of like going to the end of the line first and then working backwards to see if we can get to the bottom of the line. We need to make our upper Y value, the interval where Y is ranged from lowest to highest, go as big as 7,300. And let's be nice with it. Let's, round to the nearest 500, right? What's on the screen now is actually being hidden by this wrench box. So I'm going to mess with some things so maybe like it's coming up on your screen a little bit better. I'm going to make A larger so we can see more points. You can see more points in the video. That didn't change much, and you know what? It is bothering me that it's -14. Somewhere down here at the bottom of the screen should be the x-axis. But because we chose a number so small relative to how large the y value is, then I'm going to say let's go like -500. Something that just at least brings the x-axis and the y-axis into frame so we have our reference point and it's nice and solidly built there. You could do the steps. You could say steps by hundreds, or you could say by thousands, right? You can mess with that information, but take a look here when I click the wrench button and go back to the graph window on Desmos. There they are, the 3 dots. So you see my mouse? I'm clicking on 1, and you can click on them 2, and you can click on them 3, and they actually are lined up with the information from the table. Now, if you're with me so far, we haven't even written the equation. We did get it graphed well. We did get the points visible on the space. So now we got to write the equation. And this is Desmos code that I want you to know that you can use. I'm going to go y1 because that's the y column. And the nice thing, Desmos is already responding, saying it's a 3-element list. I'm going to use something called a regression equation, which is a high-level concept, but all you need right now is just the code. Okay? I'm going to use tilde, which is up above, wait, was I there? Up above the 1. You have to shift and then press the button right next to 1 to get that squiggle. An exponential function is written as a b to the x power. So if I go a times b, and then I have to go shift 6, I can use the keypad, which I probably should show as well. It's this button here, A with the little B subscript up above it. But if you also go Shift 6, notice how my little cursor got smaller. There's a little gray box there. I'm going to type X1. You have to put the 1 because it's the X1 column being compared to the Y1 column. And this is how regression equations work. They need both sets of data to line up. Now, the nice thing is, let me go ahead and get the keyboard out of the way. This is the function. This is the coefficient that we're going to call the initial value, A for the initial value, and then this is the growth rate or the common ratio if you connect it back to our concept of sequences. So really, the information's right there. There's nothing left to do. But if you must, what we can do is we can write the function, let's write it in function notation, f of x equals, remember f of x and y, they're interchangeable. Just f of x does something that y doesn't, and y does something when we need it that f of x doesn't. It's just a way that they're related. But right now, function notation, f of x equals and y equals are going to be the same. So I'm going to use f of x equals for DESMOS to also continue to be powerful. We have a right here. So if I write a instead of writing 6,999.96, and then I write b to the power of x. You see, maybe you do, maybe you don't, but this is now a red line going exactly over the top of that black line. The reason for that is a is now known as the 6,999.96 number, and b, should put it in parentheses, is now known as the 1.01399 number. You can use a or b. It's going to still give you the same like expression. And let me see if I can make my window here a little bit bigger for you. Oh, goodbye. There we go. All right. There it is. This is the equation that makes the population like function for Blueville, etc. That's the exponential function right there. It has an initial value around 7,000, although we didn't know that from the table, and it has a growth rate. And honestly, because there's a 1 right here, let's see if I can hover over here. Because there's a 1 right here, that means that we have a 100% of our current population, and then we're adding to it about 1.4% more people every cycle. Maybe these are years, or maybe these are decades, but the point is every cycle there's another 1.4% added to the existing population. But there you have it. We have f of x. In fact, let's go ahead and do the final thing for why we would even bother to care about this in our math class or with this extension of the real world. I can tell you how much the population is going to be in the 4th cycle, the 4th year or whatever. And all I got to do with DESMOS is just replace the x with 4. All right. That information right there says 7,399.97 people. Kind of weird to think of someone as 0.97 of a person. So we're going to round that one up. 7,400 is our prediction for the number of people in year 4 of this population count. At any point, feel free, thank you for sticking to the end, go back and watch the video, skip forward, slide through, make sure that you are able to take this information with you as you go answer your remaining questions, or even later on future lessons. This is a resource that you can use and will be very helpful for you to solve problems and to, produce results when you're up against the wall trying to find it. Thanks for watching. See you in the next episode.